Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Today we will cover second lecture of Physics 2. In this lecture we will study the remaining part of oscillation, which is from chapter number 15 in the textbook. Our main topics will be potential energy and kinetic energy, as we developed the expressions for velocity and acceleration in our previous lecture. Similarly, we have to develop the expression for kinetic energies and potential energies, and will sum up them to get the total energy of the simple harmonic oscillator. And then we will study the damped harmonic motion, as in real life not all the oscillation are ideal. There are some oscillation which is called damped harmonic oscillation, and to overcome the damping of an oscillator, an external force is needed, so that oscillation is called the force oscillation. And our last topic will be the resonance phenomena. So let us start our first topic of the lecture, total energy. But first we will find the kinetic and potential energy of a simple harmonic oscillator. The potential energy can be defined as the energy which is related with position of the object, or energy of an object with respect to a reference point is known as potential energy. And the elastic potential energy is given by U is equal to half kx square, where k is the spring constant and x is the instantaneous displacement. As in previous lecture, the instantaneous displacement is equal to xm cos omega t plus phi. When we insert the value of this instantaneous displacement over here and share the square between the amplitude term and the oscillating term, our potential energy will be equal to half k xm square cos square omega t plus phi. So this is the potential energy of the simple harmonic oscillator, which depend upon position and time. The kinetic energy of any body related with the motion of the object, and can be written as k is equal to half mv square, where this k represent the kinetic energy. Don't misunderstand this k with the spring constant. So half m is the mass of the oscillating object and v is the speed of the oscillating object. As in previous lecture we developed the expression for velocity, so put that value over here and open the square. We will get k is equal to half m omega square xm square sine square omega t plus phi. In both expression there are two different terms. This expression, the kinetic energy, the potential energy, is appear in term of spring constant and amplitude, while the kinetic energy involve the mass term and the angular frequency and the amplitude term. So to make them similar, we will insert the value of omega square. So for omega square we will write k by m. So the kinetic energy expression will be half k xm square sine square omega t plus phi. This is the kinetic energy for a mass attached spring system. Tell us that the kinetic energy also depend upon position and time. Now in order to find the total energy of the system, the total mechanical energy of the system is simply the sum of kinetic plus potential energy. So put the value of kinetic energy and potential energy which is earlier derived. So we will get half kxm square sin square omega t plus phi plus half kxm square cos square omega t plus phi. In both energies, kinetic and potential energy, the half kxm square, this term is constant. So when you take out from these two expression, so our total energy E will equal to half kxm square sin square omega t plus phi plus cos square omega t plus phi. And from trigonometric identity, this sum, the sin square omega t plus phi cos square omega t plus phi, this is equal to 1, and our total energy will be equal to half kxm square, where k is the spring constant and xm is the maximum displacement, which is known amplitude. So in the total energy we have three constant terms at the right hand side. Half, this is constant, spring constant k, this is a constant value for a specific spring, and xm is the amplitude, which is always constant. So the total energy of a simple harmonic oscillator, in which we exclude all the friction forces, will equal to half kxm square. So it is independent on position and time. So the total mechanical energy of an ideal oscillator will be always the constant. The total mechanical energy of an oscillator is indeed constant and independent on the time. In this slide, we are going to discuss the graphs of energy with respect to position and time. The potential energy and kinetic energy of a linear oscillator are shown as a function of time and displacement. The potential energy, which is u of t, and from the figure, this is the green curve which represents the potential energy. The kinetic energy is a pink curve, and the total energy is the horizontal bar, this. And these energy are drawn as a function of time for simple harmonic oscillator. Noted that all the energy are positive. We took energy on the vertical axis and time on the horizontal axis. As there is no below energy, these energies, the kinetic energies and the potential energy, are positive always. And you will observe that at t is equal to 0, the body has a maximum potential energy, which represent the extreme position of the object. So t is equal to 0, the body has a maximum potential energy, while the kinetic energy at that position at that time is 0. So the total energy is simply the sum of potential energy and kinetic energy will be equal to the potential energy at this time. When time goes, the potential energy will drop and the kinetic energy will increase, and the kinetic energy will reach to the maximum energy, which is equal to the total energy. At that time, the potential energy drops to 0, and again the potential energy increases and the kinetic energy decreases. So in a single time period or in a single cycle, you will see that there are two peaks of the pink curve and two peaks of the green curve. So in one cycle we have two peaks of kinetic energy and two peaks of the potential energy, and this will continue. One will maximum, the other will 0, and at the t is equal to t by 4, both energy will equals. Half energy will be the kinetic and half energy will be the potential, but the total energy will at every instant of time will be the same. You will see that there is an unbroken horizontal line which represent the total energy. The kinetic and potential energy oscillate between 0 and maximum, while the total energy will be always the same. In second figure, the potential energy U, which is the green one, the kinetic energy, the pink color, and the mechanical energy is drawn as a function of a position for linear harmonic oscillator with amplitude plus xm and minus xm. So from this figure, when you discuss the energy in term of position, so at mean position, when x is equal to 0, the total energy of the body is the kinetic energy. So here the kinetic energy is maximum, which touch the horizontal maximum energy. When x is equal to minus xm or plus xm, the kinetic energy becomes 0, while at that point the potential energy touches the maximum energy. So in this slide we discuss the energy of a simple harmonic oscillator. All three energy, the kinetic energy, the potential energy and the total energy, with respect to time and with respect to position. And in both plot it is understood that the total energy is remain the same and the kinetic and potential energy will change from 0 to maximum. Our next topic is damped harmonic motion. You can see the figure that we have a mass attached spring system with spring constant K, and the mass of the object is m, and a vane is attached to the mass of the object and immersed it into the water. So when this body oscillates, the water will exert a force which is known as the drag force. So what happen when this oscillate, the drag force quickly eliminate the motion of the oscillator, because this oscillator swing under water and the water will exert a drag force on it, which quickly stop the motion of this oscillator. So the drag force is a frictional force. When the motion of the oscillator reduced by the external force, the oscillator is called a damped oscillator, and the motion of such an oscillator is said to be damped. So let define some parameter to develop the expression for damped harmonic motion. Let m is the mass which oscillate vertically on a spring with a spring constant K, and we assume that the mass of this vane, the green color, is to be massless. We exclude the mass of this part of the figure, and so we will develop the equation of a damped harmonic oscillator. Water will exert a force which is equal to Fd, and this force is known as the drag force, which is directly proportional to the velocity of the simple harmonic oscillator. The equation for a drag force Fd is equal to minus Bv, where B is known as the damping constant that depends on the characteristics of both the vane and the liquid, and has the SI unit of kilogram per second. And this minus sign indicates that the Fd opposes the motion of the simple harmonic oscillator. And along with this force we have the elastic force, and is given by F is equal to minus Kx, is also called the restoring force. So the net force F equals to the sum of the drag force and the elastic force, and is given by minus Kx minus Bv equal to Ma. So this is the total force which is acting on the simple harmonic oscillator and is equal to Ma. Now, so in order to develop the equation for damped oscillator, we must express the velocity and acceleration in term of a position. So our equation will be m, and for A we write the double derivative of position with respect to time plus the drag constant, and this is the velocity which is single derivative of the position with respect to time plus Kx is equal to 0. So this is the second order differential equation, and the solution of this equation is given by x is a function of time is equal to xm exponential term e power minus bt divided by 2m into cos omega prime t minus phi. So if you compare this expression with the expression of an ideal oscillator, this is the extra term, and this term occurs due to the drag force, and the omega prime is not the same as the omega. This is the frequency of the damped harmonic oscillator and is given by omega prime is equal to under the root k by m minus b square divided by 4m square. So this is the extra term which comes in the case of a damped harmonic oscillator. If we put b is equal to 0, then this omega prime will equal to the natural frequency of the harmonic oscillator, or if we put b is equal to 0, then both equation will reduce to ideal frictionless oscillator equation. So if we study the energy of the damped harmonic oscillator and we compare it with the undamped harmonic oscillator, so it is clear that the energy of the undamped we have developed earlier, E is equal to half kxm square, while the energy of the damped harmonic oscillator E is equal to half k e power minus bt divided by m into xm square. So this is the extra term for in the damped harmonic oscillator, and from the figure it is clear that at t is equal to 0, when the object start from the maximum amplitude, as time goes on the amplitude will reduced. So at t is equal to 6 seconds, you can clearly see that the amplitude is much smaller than at t is equal to 0, and this is the exponential decrease which is indicated by this negative sign. Initially we have the maximum displacement, and as time goes the amplitude decreases exponentially, which is indicated by this negative sign. So if the oscillator is damped, the mechanical energy is not constant but will decrease with the time. So this energy depends upon time. Our next topic is force oscillation, and in this slide we will discuss the difference between free and force oscillation. The free oscillation, a body which oscillates with the natural frequency. Consider a person swinging in a swing without anyone pushing it is an example of free oscillation. Forced oscillation. The oscillation of a body due to a periodic force, that is, if someone pushes the swing periodically, the swing has forced or driven oscillation. Two angular frequencies are associated with a system undergoing driven oscillations. One, the natural angular frequency omega of the system, which is the angular frequency at which it would oscillate if it were suddenly disturbed and then left to oscillate freely. The second angular frequency omega d of the external driving force causing the driven oscillation. In force oscillation, the resonance phenomena may occur, but first we write the expression for instantaneous displacement for the forced oscillator. X of t, which represents the instantaneous displacement, is equal to xm cos omega d t plus phi, where xm is the maximum amplitude and omega d represent the angular frequency of the forced oscillation system. The resonance condition, when the forced frequency is equal to the natural frequency of the oscillator, or when the ratio of the forced frequency to the natural frequency become 1, as the resonance phenomena, and this condition is the resonance condition. At this condition, the amplitude of the oscillating body is the greatest and will be low at some other value than omega d. In the given figure, three different forced oscillation in three different material mediums. As you see that the value of b is changing, so this represents the three different material medium. The resonance peaks occur. These are the resonance peak where omega d divided by omega is equal to 1. So you will see that at this condition the peaks are occur, and when you move left or right to the ratio omega d divided by omega, you will see that there is a decrease in the curve. There is decrease in the amplitude. So the amplitude of the oscillator will be maximum when this condition is occur. This is the amplitude of the force oscillation. It will maximum only when omega is equal to omega d, and the curve will reduce as you move left or right of this peak point. So these are the resonance peak, and the phenomena is known as the resonance phenomena. So let's sum up what we have studied in this lecture. We study the energy of simple harmonic oscillator. First we write the expression for potential and kinetic energy, and then sum them up and calculate the total energy of the simple harmonic oscillator, which was the ideal oscillator. And the energy of the simple harmonic oscillator, which is unforced, is independent on the time and position. Then we study the damped simple harmonic motion, and also study the energy curve for a damped harmonic motion, in which the total energy depend upon the time and position, and the energy is exponentially decreases. Then we study the force oscillation and the resonance phenomena. In order to continue the motion in any fractional material medium, we need an agent which continue oscillation, and in that force oscillation the resonance phenomena may occur, in which the force oscillation frequency meet with the natural frequency of the oscillator. In next lecture we will study wave and its types. Also we will study a tool in which two waves can be added and will discuss the resultant when we treat two waves at a single point and at a same time. Hopefully you will understand the lecture, and if you have any question you can contact me at my email. Thanks and Allah Hafiz.